Okay, so we are in Statistical Rethinking, second edition. We're in chapter 11, and we're on question 11M2. And so here's the question. So if a coefficient for Poisson regression has a value of 1.7, what does this imply about the change in the outcome? Okay, so first let's get acquainted with a Poisson regression, what it might look like. So we might have an outcome variable y distributed as Poisson, and a Poisson distribution has one parameter, lambda is what it's usually called, and lambda represents the expected value of the Poisson distribution. It also represents its variance, I believe, which is peculiar to the Poisson. So now we want to make a linear model where we're trying to predict the expected value of our distribution of lambda. Okay, and so we typically use, for our GLMs, we use a log link function. So in other words, we take the natural log of lambda, okay, and we set that equal to our linear expression. And so here I'm just using an intercept and a single explanatory variable with its corresponding beta coefficient. Okay, so we can write this part right here, our linear expression, a little bit differently. So if we exponentiate both sides, getting rid of this natural log, well, now we just have lambda equals the exponentiated a plus, or alpha plus beta x. And I can rewrite this, which might come in handy, also as e to the alpha times e to the beta x. Okay. So our question, well, generally our question is what happens to lambda, to this value, which again is the expected value of our distribution, okay, or of our data, if our explanatory variable increases by 1 unit. Okay, so how, well, okay. So the way we want to think about this, well, the way that, to be honest, the way that we want to think about this is we want to take our linear expression here and just compare what happens when I have beta x plus 1 versus just beta x. Okay. Now, now we exponentiate this, or I mean, there's other ways to do this, but this is, I think, the easiest way to see this. So, so I'm just comparing my linear model when x is x versus when x equals 1, and I'm taking the difference, right? But we have our exponentiated model, so I have this, okay? And it's, well, so we have this, okay? So I can rewrite this expression right here as the exponentiation of the first component divided by, so in log world, minuses become divisions, okay, divided by this second part here, okay. So now I'm going to rewrite both parts here in this kind of notation, okay. So I have e to the alpha times e to the beta x plus 1, and that's being divided by e to the alpha, e to the beta x, all right. So I'm going to continue to rewrite. So notice that they have a common e to the alpha, so those just drop out. And then I'm just going to distribute this beta over the x plus 1. So now I have e to the beta x remaining in the denominator, and then I have e to the beta x plus beta in the numerator. Okay? But again, I can rewrite this guy as e to the beta x times e to the beta. Well, now again, the numerator and denominator have in common an e to the beta x, so that just drops out, leaving e to the beta. Okay, so what does that mean? So that means that that if we modify x by 1 unit, then the proportional change between lambda x plus 1 versus lambda x is just e to the beta. Okay. So in other words, there is a multiplicative effect happening to beta here, all right, because we're taking a proportion. Okay, so so more specifically to the question, a 1 unit change in x results in a e to the beta change in lambda x plus 1 compared to lambda x. So if beta equals 1.7, then our proportional change to lambda x plus 1 is e to the 1.7. Okay, which is 5.47. So I guess that is it here.